Well, hello everybody. My name is Andy Cotgreave, and I'd like to welcome you to today's live stream from Tableau. Thank you very much for joining us today. Have you ever wondered how you get data from space? Well, I have. And today I'm really, really honored and excited that we've got somebody to answer that question because they know the answers to those questions very intimately. I'm joined by Roberto Orosei, who's research scientist from the National Institute of Astrophysics in Italy. And he's most well known for the work he and his team have been doing to discover liquid water on Mars. That is pretty astounding. Now, this is a story of analytics, of hacking spacecraft and data collection that actually bears some realities to the day-to-day job of analysts like you and me, but here we're on an interplanetary scale. So we're going to talk for about 20 to 30 minutes. And if you have questions, please type them in the Facebook comment box, and we'll try to address those either at the end or as they arise. So with that, Roberto, welcome and thank you for joining us. I thought, could you just start by giving us a brief overview of the mission and the discoveries, and then we'll dig into some of the details as we continue.
Thank you, Andy, for inviting me. Yes, Mars Express was the first interplanetary mission built in Europe, and it successfully reached Mars in the late 2003. On board the spacecraft, there are 7 experiments, and one of them is the radar I'm the scientific manager of, Marcis. Marcis is a subsurface sounding radar similar to ground penetrating radars used on Earth. It uses the property of low frequency radio waves to penetrate into solid matter and produce reflections when the dielectric properties, the nature of the material changes. So through this method, one can see the stratigraphy of subsurface, and in the case of Marcis, you can reach as deep down as, well, almost 4 kilometers. And well, Marcis has been working since 2005, actually, and collecting data since then. And only after several years of data acquisition and analysis, as you mentioned, also hacking the onboard software a bit, we were successfully able to demonstrate that there is liquid water on Mars. And on Earth, that's typical of, radars are used to this purpose on glaciers in Antarctica and Greenland. And the telltale sign of water, the presence of water, is a great enhancement of the strength, the subsurface echo. Water is the most reflecting natural material. And when you start seeing echoes that are even stronger than the echoes that come from the surface of the ice, this is the typical sign that you are flying over water. Of course, proving the same on Mars is not as easy as it is on Earth, because on Earth you can always check by yourself if this is true. Yeah. And this is almost taken by now, it's a common procedure. But on Mars, you're not sure of what is the content of the polar caps. It's not necessarily only ice, and we know there is dust, and we know there's CO2 ice, and this might affect the way in which radar waves are reflected. So it took a lot of work to model this process and to be able to exclude other explanations for what we see.
Yeah, brilliant. So just on screen at the moment, I've got one of the pictures from the paper, which is the proof. And this is the image that is talking about those loud reflections that come from an ice-water interface. Is that right?
Yes, that's correct. They are highlighted in blue, in light blue. And yeah, those echoes coming from the light blue areas are at least 10 times stronger than the echoes that come from the surface of the ice, which is really unusual.
Yeah, and I think we'll talk in a little bit about how you go through the challenge of reducing all the other things it could be, and you know, actually realizing that, well, because it can't be anything else, it has to be water. And could you just explain also the area of the planet you discovered and how big a lake we have found?
Yeah, the lake, let's call it like that for short. Someone would insist that it should be more correctly called a body of subglacial liquid water, but it gets lengthy after a while.
Is it okay if we call it lake?
Yeah. Okay. It's located beneath the South Polar Cap, and which consists of a kind of terrain, or which is called the South Polar Layer deposits, which is a thick layer of dust and mostly ice, water ice, intermixed with dust in a stratified structure. This is the result of climatic change on Mars, in which the position of material at the pole changes its nature. Sometimes it's icy and sometimes it's dusty. And this change is due to the prevalent climate at the time at which the process takes place. So you have this layered cake structure of plain parallel layers that extends in places for more than 3.5 kilometers. But in this particular area is about 1.5 kilometers. And the lake itself is not very wide, is about 20 kilometers across. Compared to the diameter of the polar cap itself, which is almost 2,000 kilometers, is quite tiny. But finding it was, let's say, in a sense, a strike of good luck, but also was the result of extended work to improve the quality of the data above this particular area.
Brilliant. And before we get on to that quality and the data experience of this, how profound a discovery is this? Because it had a big splash when it was announced last year. What does this mean for Mars and further studies?
Well, when Mars Express was being planned in the second half of the 90s, the mantra for the exploration of Mars was follow the water. It was realized over the decades since the Viking mission provided a complete mapping of the surface of the planet, that Mars in the past had to be warmer and wetter than it is today. Today, Mars is unlivable on its surface. The atmosphere is too thin, it's too cold, and there's very little humidity in the atmosphere, and all the water is frozen in the poles as the polar caps. So, but we see dry riverbeds, and we see many other landforms that had been carved by water. And to explain this, to reconcile this with the current Mars, we had to hypothesize that in the past, the atmosphere had to be much thicker, denser, and being made of CO2 produced a greenhouse effect that raised the temperature above the melting point. So water on Mars used to be liquid in the past, but the planet being smaller than the Earth and its gravity pull being weaker, the atmosphere was lost over time, and so Mars froze over. And the finding liquid water on Mars today means to find a place where life can conceivably exist today. Mars, as I said, has been temperate for a period of perhaps 300 to 800 million years, depending on estimates, which was a sufficient time on Earth for life to develop. So Mars had similar conditions to the Earth, never mind the atmosphere. Life was born in the oceans, and there were probably lakes and rivers and maybe seas. So it's conceivable that life could have been born on Mars too. And actually, this is the big question. Did it happen?
Yeah.
Of course, finding evidence after 3.5 billion years, then after Mars changed its climate, it's difficult. But if you find a place where conceivably a living organism could survive today, then there is the place to look.
Yeah, that's fantastic. So obviously a big, profound discovery, and maybe a future spacecraft can go and start answering some of these questions. But let's talk about the data, because I think there's just some great stories here. First of all, most analysts watching this live stream are using the latest technology, super fast databases, software written in 2019 or maybe 2018 or maybe prehistory of 2017. That's old software. What kind of data collection and technology are you using with Marcis?
Well, it's the dirty little secret of all space missions. By the time the spacecraft is on the launch pad, its technology is already obsolete. Because the development time of space missions ranges from 5 years, as in the case of Mars Express, which was a fast one. That's why it was called Express in the first place, to 10 years and sometimes more. Developing a space mission is a painstakingly slow process that requires a lot of testing. And when the mission is decided, it's decided to build a spacecraft, the technology has to be in place. There is no risk taking with waiting for new developments. So the components are the ones that are available at the time, which for Mars Express means 1997.
I find that amazing. I mean, I'm sure a lot of people on this watching this maybe weren't even alive in 1997. I was just starting my career, and I didn't even. Well, it was modems. We were connecting to the internet on modems, and the browsers were just about developing. Right? I mean, that seems amazing to have gone back so far. So we're on old technology, and then you've got a spacecraft orbiting a planet, which is orbiting the sun, communicating to another planet orbiting the sun differently, and there's many experiments on the spacecraft too. So how do you even get data back to Earth?
Well, this is the main bottleneck. In fact, when you design a space mission, you have to make sure that you are able to deliver enough data to the ground. This is not only a matter of having the antenna pointing to the Earth and transmitting. Of course, data rate is very low for Mars Express. The bit rate between Earth and Mars is of the order of a few megabits when we are lucky. But even within the spacecraft, it's really low because the spacecraft computer can handle a data rate coming from the instruments of the order of several tens of kilobits per second. And that forced, for example, the designers of Marcis to do a lot of data processing within the experiment. We were forced to deliver data that were aggregated and thus reduced in volume by a factor of several tens or 100.
So this is a really key part of the conversation that thrills me. Is you were sending radar signals into an area of Mars and analyzing the echoes that came back, and it was those echoes. Looking at those echoes enabled you to find these bright reflections. That's right. And then, by the initial design of the experiment, the data coming back was aggregated too much. Is that right?
Yeah, that's correct.
Yeah.
You usually sum together something between 100 and 200 echoes, depending on where you are in the orbit, the frequency you're using. And these echoes have to be summed in perfect synchronism, in the sense that any vertical motion of the spacecraft has to be compensated by shifting the signal in time from pulse to pulse before you sum them. Otherwise, you tend to cancel out information. And this is done by predicting the velocity of the spacecraft. Whereas you know that you can know the real velocity only after the fact. So there's an intrinsic error. And so that, for us, meant a lot of extra work, and is very much the main reason why it took us 10 years before we could get to the result. This
is so good, because as a data analyst, I could just go to my IT department and say, can you change the aggregation level of this data source, and then they will fix it, and then I get the new data within hopefully a matter of hours. But you've got this discovery where the data is not working. So what were the methods that you did to force the spacecraft to give you disaggregated data so that you could look at it in more detail?
Well, there is a touch of fate and luck in this story. It's almost a legend, I would say. I've been told that during the making of the experiment, of the instrument, and the motherboard had a few free slots in which some extra components could be inserted, and someone had the thought of adding some onboard memory as an extra safety in case something in the processing didn't function. and was also thought as a way to record the data before they were aggregated, to compare them to what comes down after aggregation, to make some tests. So that was a last-minute decision, and there weren't even the components to do that, but apparently they were scavenged from another project. And there is also this moment in time in which these memories were carried across a passport control in an airport in the pocket of a person that didn't even remember that he had them. And when he remembered that he had to give it to the person that was staying outside, he threw it across the passport check. So you understand that we are well before 2001 and 9/11, because if something like that happens now, you would be immediately covered by agents, police agents, jumping you. But and apparently the good catch of the other person ensured that the memories survived and were finally added to the experiment. So at first they were used only for control, for a few tests, just recording 100 or 200 echoes, the same amount that is usually aggregated. But when we realized that the problem we had was that the data were too aggregated, that we were losing information, that we were not be able to clearly detect bright radar spots because the bright reflections were averaged with other not so bright reflections, and we were not able to tell what we were seeing, that someone thought of those memories, and by which amount to the astonishing to 16 megabytes. But wow. 16 megabytes of memory were sufficient to record of the order of 3,000 echoes without aggregation. Except that the spacecraft the instrument could not do that. And to be able to do that, our engineers decided to cheat a little bit and tell the experiment they were flying at a different altitude. And so because the level of aggregation is decided based on as I said, altitude, frequency, and such, by fooling the software and giving it fake parameters, flight parameters that were meant to make the spacecraft compute an aggregation number that was much greater than a few hundred, they would just be compressing together those 3,000 echoes altogether. But at the same time, those echoes could be saved in the memory and retrieved at a later time through the spacecraft mass memory. So by doing that, we were just getting a coverage of a strip of data about 100 kilometers long along the spacecraft ground track, as it's called. And that was enough when we were zooming in on the right place to let us first characterize the reflections very clearly. We were getting repeatable measurements, what we were not able to get for years and years. So the bright spot was always there, and it was always bright when we flew over it. And finally, by waiting for orbital mechanics to do its work, because unfortunately the spacecraft trajectory evolves in a very complex way, so you don't get to observe the same place very often. It took us 3.5 years to build up enough data, to be finally able to do some analysis. Then we had it. We had about 27 observations, so 27 strips, 100 kilometers long, crisscrossing over this area, and we were able to finally analyze and see what we were hoping to see. And that was that was the end of the story, or the beginning of another one, in fact.
And those are the strips we can see on the screen here. Is that what?
That's correct. They are color-coded, of course, for the brightness of the reflection.
Yeah.
And blue, of course, is the bright reflector.
Right. That's. I think this story is great because, again, if I have a need to change the data that I've collected, then I just go and change what's going on in the underlying database, and I install more memory into my motherboard if I'm really desperate. I can physically touch these things, and yet the ingenuity of what you and teams, and I mean, there are many stories like this from space science, where you've got to fix it remotely with the components that are available. So I think that's a great piece of work from your engineers. And you talked to me on our pre-conversations about whether this was official work or not. Can you talk about that?
Well, yeah. This is one of the things in which, unfortunately, management was not really part of the picture. It was voluntary work. One of the engineer that found the way to fool the onboard software was working for free. He was just so committed to the project that even after moving to a new company, he had the skills and the expertise. He was the only person that could do that, and he wanted to do it for free. At the beginning, it was almost well, it was not even for this specific application. He just wanted to toy with the instrument because he was just so fond of that.
Yeah.
And he was helped also by our operation manager that at the time, unfortunately, was surviving on soft money. So again, a person that didn't have a fixed position that, well, this is a typical Italian problem, I would say, the work instability, but I'm sure it's not only in Italy that this happens. But we were able to keep him, and finally he got a real contract now.
Well, I love that. I mean, and again, that's a story. I hear those stories of passion and determination to work around problems, you know, even on terrestrial space. But I just think hacking the spacecraft is pretty astonishing. And you describe the orbit. There are many different experiments on the spacecraft. So it's even getting the data is about being in a queue and finding the time to get your data for your experiment. Is that frustrating or just part of the field you're in?
Well, it was a nightmare. This was probably the hardest part of the mission, at least at the beginning. You know, there are several cases in which a space mission is found to be defective in some way, a spacecraft, after the launch, and you have to live with that. And in the case of Mars Express, it was the solar panels that unfortunately were assembled and cabled in an incorrect way, and so the panels were providing only 2/3 of the power they were expected to provide. And that meant that the 7 instruments could not be operating at once. They had to be switched on and off in sequence. And that became, first of all, an operational nightmare. I think that the expression that the spacecraft operation manager used was wrestling with an octopus or something like that, because it was trying to reconcile all the different requirements from the different experiments and trying to make everybody happy. And then, of course, the scientists themselves were part of the decision process, but some of them were really, really, well, can I say aggressive? But okay, everybody was convinced of the great importance of their own measurements. And so it was very confrontational at times. And it was really something to be seen, to be understood.
Yeah, I can imagine. No, I think I am seeing parallels with a lot of business intelligence and data projects there. So you've got your data, right? And you're looking at it and thinking, yeah, this reflection is pretty much water on Mars or an underground body of liquid water. So you then know that this is a profound discovery. So you've got to discount everything else, right? How do you go about that with the data you have? And I mean, you do write about this in the paper, but I just wondered, you know, how you go about that process, and at what point do you feel confident that you can go to the world with your data and say, this is it, and then expose yourself to all the media and academic attention that brings?
Well, once we got all the data, it was not even easy to compare observations, different observations. Unfortunately, the experiment is not calibrated. So because the antenna is 40 meters long and you cannot test it in any facility, any conceivable facility. And this means that we had no way to convert the voltage measured inside the instrument into some physical unit or parameter like reflectivity or something that can be compared from orbit to orbit. And so we had to struggle very much just to be able to find a system to normalize the data and make them comparable from orbit to orbit. That was step one. And when I found a way to do that, that was my peculiar contribution to the whole work, was when I realized that, in fact, there were regularities that were allowing a calibration that could be somehow justified. And I saw that the level of power of crossing orbits was the same over the same place, so that you are really able to compare apples to apples. Well, that was a big moment. And there is when I realized we can make it. And actually, I'm thinking of the scene in Young Frankenstein. You know that movie? When the professor flips through the book of his ancestor and says, "It can be done," something like that.
I remember that.
Yeah, Gene Wilder, I think.
Yeah.
And I felt a bit like that. But
that's great. So just to clarify, right, on screen we've got a picture of Mars Express, and the long antenna is the Marcis experiment. Is that right?
That's correct. Yes.
Yep. But just so you had data, so you got your data, but then were you in this period where you're looking, going, this data just still isn't good enough because you can't calibrate it, or did you always anticipate that calibration problem?
Well, we were not. Well, we were so busy getting the data, we simply left everything on the processing and the analysis to after we got the data. So we start fresh. And well, this is a bit of personal thing. Unfortunately, the final acquisition, the final observation took place only a few months after the original designer of the experiment, Professor Giovanni Pipcardi, the original leader of the team, passed away in July to August 2015. So essentially, by the time we got all the data, the team was in pieces and we had to restart everything from scratch. And that, in a sense, provided the opportunity to try something fresh. And so finding a new calibration was the first step. The second was to define a way to, well, it's an inversion problem, as it's called. You have measured quantities and you have to derive the physical parameters of the thing you're observing that determine the observed quantities. And this is, by definition, a tricky thing to do. And the previous mathematical approaches that were attempted failed, essentially. So we had to restart even there. And we simply decided to go on a more empirical approach, rather than trying to be rigorously mathematical to do the full inverse problem, and which was producing big error bars, and we would never able to firmly constrain to some physical parameters that were very essential, but were essentially impossible to know, like the quantity of dust in the ice, which is, we simply decided to go for it by modeling, forward modeling. So we had a model to study how the strength of the echo as a function of the composition of the ice above it. So the percentage of water ice, dust, the CO2 ice. And we could vary those parameters at will. And we simply decided by maybe it could be called a brute force approach to try every possible combination. We explored the parameter space, and we were saying, so by changing what are the combinations that provide the same echoes, the same echo strength that you observe? And they were those that required a permittivity of the material under the ice, beneath the ice, that was much greater than that of common rocks that required water, essentially. So that's the way we did it. We would not try to fully solve the inverse problem. We rather decided to do the forward modeling and do a sort of statistical approach, say, how is it likely to get this particular echo strength given all the possible combinations of the parameter? And you get that only the high permittivity makes it possible. Other effects like resonances or other geometric effects could be ruled out eventually. And so we went by exclusion, let's say. We removed the impossible, and then we were left with the possible, as Sherlock Holmes would have it.
That's absolutely brilliant. Right, well, we've actually gone half an hour already. I'll just ask maybe a couple more questions, and if anybody does have questions they wanted to ask Roberto, please type them into the Facebook comment box. We'll get to those. So this is obviously a great story, and you know this has been hugely covered, right? I particularly love this data analysis story and the data acquisition. Is this I mean, you must be involved in quite a lot of different spacecraft, or you must be aware of them. And are there any other general challenges or stories you've come across that about how other people have faced challenges and had to deal with the data analysis challenges on other missions?
Well, yeah, that's true. I've been involved in several space projects by now. And when you are jumping into them from the very start, you see all the life cycle. And of course, the big thing is always fitting within the resource envelope. This is the very big bottleneck. And in particular, you have power, you have mass, and you have data rate. And these three quantities are going to challenge you all the time. You could think of the best experiment in the world, and you could have the most brilliant ideas on how to use them. But if you don't fit in the resource envelope, it's not even worth doing it. So sometimes you just have an experiment which is too good, in the sense that, yeah, you can do a lot of things, but then you cannot actually do them. And so you could even risk of being left on the ground instead of being in the payload if you don't develop a reasonable compromise between what you can do and what you want to do.
And is that's a big challenge that you're facing, or I guess people are facing right now, because we found this water. Well, how do we go and test the water? You have to send a spacecraft that can drill 1.x kilometers beneath the surface. Now, we've just been doing that in the Antarctica, haven't we? There's some very deep drills. I think it was 12K they've managed to do, but we can physically get human beings there. I mean, it's still remote, but we can physically do it and adapt. Is it even possible to send a drilling machine to Mars to come and look at your water?
It will take time. And even now, I have to apologize for a moment. What do I do? There's a phone ringing. I can just pretend there. If you don't mind,
keep going. We can barely hear it.
Okay. First of all, space missions have a very long lifetime. They take from 5 to 10 years to develop, and then they have an operational lifetime of sometimes a decade or even more, like Mars Express, which has been orbiting Mars for more than 15 years by now. But when you really I'm sorry, I was distracted by the phone call.
It's always very hard. So can we send a spacecraft to go and drill into this?
Oh yeah, sorry about that. It kept ringing. So it means that we now are planning what will take place in the next 20 years, and it's not really something that will change anytime soon. The time will be the same. The time period it takes to build a spacecraft operated, it's the same. So there will be no drilling on Mars for a generation. That's for sure.
I can imagine. Hopefully we'll still be around when it happens.
Well, look, hopefully we will have time to find a way to drill in the first place, because we don't know how to do it yet.
Well, hopefully we'll be alive when somebody makes that happen. Well, look, we've gone for 35 minutes, and obviously there are people trying to get in touch with you. So if we got a question or two, but I'm going to we'll follow up maybe with those questions and try and get some answers afterwards. But Roberto, thank you for giving us the opportunity to talk to you. I just love this story. I think it's been incredible learning about it. Congratulations on finding water on Mars. So yeah, thank you very much. And we will see you soon. And you may now go and answer your phone call.
Thank you so much. Thank you. It was a pleasure. It was a pleasure.
Thank you very much. Okay. Bye, everybody. Thanks, Roberto.
Bye-bye.
Bye.